Log on, tune in, find out. Another good idea from Cambridge.
For today is Alexey Bondal of Steklov Institute, and the title is Minuscule, Varieties and their Degenerations.
Thank you. Well, I give first some motivation, and this motivation from real physics, not string theory. Real physicists care about only one model, and this is the standard model, the one which describes those particles which could be observed in up to now. And the standard model is a gauge theory. So I give some introduction for mathematicians. Well, first of all, it's like in mechanics. There is classical mechanics and quantum mechanics. I will describe the classical part of the story in the very short terms. So there are various fields. Actually, there is two types of fields. There's so-called gauge fields. In this theory, and matter fields. Well, we first start from some manifold, which is our space-time, so it's endowed with a metric, the signature 3,1, and actually we need to fix some spin structure on it. Gauge field is a connection on some principal G bundle. Oh yes, we also fix some group G. When some extra structure will appear. So P is a principal G bundle. G is G for the standard model. This is called gauge group, and this is U1 cross SU2 cross SU3. Oh, sorry. Which everybody knows. So we need to fix some connection on it. Components of this connection with respect to the decomposition of these groups are called various fields, various particles after all. Matter fields are sections of some vector bundle, and this vector bundle is related to representation, so we need to fix. So we fix group and we fix the representation. So if we fix the representation, we can take the associated vector bundle E, which is just V tensor M, V cross M over V cross P over G. So this is a vector bundle over M. So this matter field is a section of this vector bundle E, tensored with the spinor bundle S. We fix some spin structure, and actually also tensored with some three-dimensional space. Well, the reason there is no mathematical reason to tensor with this three-dimensional vector space. This is responsible for generations of particles. So generations. So there's three generations, and that's why we tensor with this three-dimensional vector. People say that if you explain why it should be tensored with this vector space, you got Nobel Prize. So I give some idea how these components might appear here, but unfortunately in my picture it's not just three-dimensional vector space for every particle. So
Is V just the standard representation?
V? No. V is actually the sum of 5 irreducible representations. One of them, I don't remember all of them, but I will explain how to get them from a little bit different picture. So this 5-dimensional, for example, it's not 5-dimensional. This is a representation where I take the standard representation for this component SU2, tensor it with the standard representation for SU3. But for this guy, you should take 1/6. So physicists put here somewhere 1/6, meaning that it's actually a representation of 6-fold covering of this group. You know, physicists don't care about difference between Lie groups and the algebras. So this is a typical typical presentation. It's actually the biggest one. So this is this 3-dimensional is responsible for quarks, because this is a strong interaction group, this is a weak interaction group, and U1, which is in the mixture of these two components, is responsible for electromagnetic interaction. So there is natural questions why we should take this group, why we should take these representations, right? So what physicists do, they say, well, this is a field theory, so it's an infinite-dimensional classical mechanics. The space, so the manifold is infinite-dimensional, and this manifold consists of this. So let's denote this section. So we take section of this bundle, let's denote it by S, and we consider the connection, let's denote it by A, connection in the principal bundle. So we consider the infinite dimensional variety of all these guys, A and S, infinite dimensional manifold, and there is some Lagrangian, which I don't bother to write down. It's basically unique Lagrangian, which you can write down so that it would be renormalizable, which is a function on this manifold, say T. It's a function on this manifold called Lagrangian, and then, like in classical mechanics, you have some equations of motions and so on. Of course, the most interesting part is about quantization of this picture. So what I would like to describe is something which might help to understand how we should mathematically do this, and also how to fit this picture into the string theory. The reason why physicists don't believe, why they don't care very much about string theory is because there is no way to fit this picture into string theoretical constructions. So it's still an open problem how to do this. So I hope I will contribute a little bit to this direction. So representations. Well, it's also was done by physicists. They started thinking how to understand this group, and they embed this group into bigger group called grand unification theory. And this grand unification theory group is SU5. The embedding is very simple. You take 2x2 matrices, 3x3 matrices, and embedded is this kind of blocks. So this is SU2, this is SU3, and the U1 could be embedded into this guy, so it would commute with these two blocks and still be in SU5. So exponents of this embedding is this. So this exponent of this gives you U1 component. And this is SU2 and SU3. So this is the embedding. And if you consider this group, then the corresponding representations should be just the dual to the standard one. which is C5 star, and the weight squared of this 5-dimensional representation. So when you restrict these guys to this subgroup, you got these representations. But of course, we can ask why we should take this group and this representations. And the answer is that we can continue. It's just the first floors of the tower. So because this was already Grant unification theory, the next group was also called Grant unification, because it was Grant already at the first step. So let's call it Grant unification. And this group is SO10. And in fact, you can continue. To understand this, you should consider exceptional series of Lie groups or Lie algebras with the corresponding de-inking diagram. I will start from E7.
Alexey, what's the representation for SO10?
For which? For SO10? Well, there is a choice, but I will fix some, just one representation for some reason. I will explain later which one. So you start from E7, and I explain why E7 a bit later. And this tower, so this is the highest floor of the tower, and the representation is the fundamental representation corresponding to this vertex. Then we remove it, and the next one is this one. And then we can remove this guy, and then we got this picture. So this is E6, this is D5, and this is actually SO5, SO10. So this this Grant unification appears at this level. And then when we remove this guy, we got this picture. And this is the de-inking diagram for A4, which means SL5, which is of course just the complexification of those groups. I mean, physicists can consider compact groups, but of course mathematicians prefer to complexify them and consider a unitary structure at the very end of the story. So because we remove this vertex here, we should consider the adjacent one, which is this one. So here we consider this fundamental weight, and if we now remove this guy, then we got just this picture, and then there's two adjacent weights, this one and this one. And this is the group, the corresponding group is SL2 cross SL3. So you can see it's almost the complexification of the standard model group. And in fact, this U1 or C star factor will appear also when we consider general descent along this tower and also some others. So mathematical.
Why didn't you start at E8?
Why not E8?
Yeah.
Because E8 does not have good representations. And these good representations are minuscule. So let me now introduce them. Minuscule representation. So we have some, say, semi-simple Lie group, G semi-simple Lie group. Representation is said to be minuscule if V. If V irreducible, and second, well, V is decomposed into the sum of its weight spaces with respect chi, where should be this chi? Upstairs or downstairs? Maybe downstairs. Where chi are characters of the maximal torus. So in T we fixed the Cartan torus. so these are weight space with respect to the Cartan torus. So it's called minuscule if so it's actually some finite subsets in here, right? So chi belongs to some finite subset if S is and S is the W orbit, where W is the Weyl group. So minuscule means that S is transitive with respect to the action of W. Just one W orbit. So there's two properties, this one and this one. So it follows that if V is minuscule, then it's actually a fundamental representation. Which means that it corresponds to some fundamental root of the root system. And fundamental roots corresponds to vertices of Dynkin diagram. So here are examples of minuscule fundamental weights. In fact, for E7 is the only one. There is no for E8, and that's the answer to your question. For E6, it's of course two, this one and this one. For D5, it's this, this, and this. For SLN cases, all of them are minuscule. And here it's two. Now, being a geometer and not representation theorist, I quickly come to geometry, and this is given by Borel-Weyl-Bott theorem. Borel-Bott-Weyl theorem, which claims that every irreducible representation of a semi-simple group is actually a global section of some line bundle on some homogeneous space homogeneous with respect to the action of this group. And this X is actually just the orbit of the highest vector. So we take the orbit in the projectivization of our vector space V. Then we should put do here. So this is the definition.
Alexey, isn't it Borel-Bay?
Pardon?
Andrew Bay, not Herman Weyl.
What?
It's the other Andrew Bay, not Herman Weyl.
Oh, yeah. Yeah, it's a problem. In Russian, they sound the same. written and sound the same. Thank you. So it's a, I mean, this is a construction which works for any irreducible representation, but we will apply it to minuscule representation. So minuscule representation is a group with some representation. If we consider variety, then we should consider three things, three guys: group, the variety, and the line bundle. In this case, the line bundle is just the restriction of O1 on the projective space. We just restrict it to X. So this is minuscule variety, and this is minuscule representation. So we should take into account the group and the line bundle, not just variety itself. Okay. Now, and of course, having this, we can easily reconstruct this, and that's what I did here, and also to go the other way around, and that's what I did here, right? So it's this data gives you the same as this data. Now, there is a nice construction. As you remember, there I come from up to down, and there is actually general construction for minuscule varieties or for minuscule representations. It's better to start with representations. So assume we have GV, which is minuscule, and I want to construct new group and new representation, and this would be called minuscule descent. So I need to construct, not variety, first some group, and this will be group L prime, and will be some representation. So what is this? Well, we need to fix, well, first of all, this X is actually quotient, I mean, it's a projective homogeneous variety, so it's a quotient of X by some parabolic subgroup P, which is also could be called P is a minuscule, and in fact it's a maximal parabolic subgroup. in G. But again, not the other way around. It could be maximal but not minuscule. Maybe first I had to give the full classification of them. Actually, I already almost done it. So in n case, it's just any weight, any fundamental weight. Yeah, I will be interested only ADE series. So G is ADE. And the reason is that there are more minuscule varieties for other series, but all of them geometrically are in the list of ADE series. And just, you know, to describe theory in more general setting of not only simply connected case, it's kind of more some boring details appear. So it's assume this. There is no more minuscule varieties, and for that reason, we can restrict us to this case. So for D series, as I said, the Dynkin diagram is this one, and minuscule weights are this one, and this one. And for E series, I have already described them. So that's the whole list. Now, this minuscule descent works in this way. We consider this parabolic subgroup, and this Levy. So this parabolic has some Levy group in it. So let's L be Levy subgroup in the parabolic one. Then this L is actually has decomposition into L prime. So at the level, and I will also denote by, say, by this letter G, the Lie algebra of G, by L, the Lie algebra of L, by P, the Lie algebra of P, parabolic subgroup, and so on. So if you consider Lie algebra of this Levy group, then it is the sum of L prime plus one-dimensional center. So C is in the center of this L, and this L prime is semi-simple Lie algebra. And let's L prime be corresponding semi-simple Lie group. Simply connect, yes. So corresponding Lie group. So then we can take, let's denote this CZ. So this Z is an element in the center, and we can consider action of Z on our Lie algebra. So Z decompose our Lie algebra G into three components. It's a grading with three steps. So it's G minus 1 plus G0 plus G1. So this is the, with respect to the adjoint action, this element Z on this guy acts with eigenvalue 1, 0, and minus 1. Our parabolic subgroup P, this guy, is the sum of G0 plus G1. And G0 is actually nothing but this Lie group L. So we can consider the action of L prime. So this is the Lie group. I mean, this is Lie algebra, and this is Lie group L prime. So we have, let's say, L prime is the Lie of L prime. So the minuscule descent is the transfer from this pair to a new pair, which is L prime and G minus. So the claim is that this is again a minuscule representation. Not very hard to prove. Under the condition that we are in ADE series. If it's not ADE series, then here we might have 5 components, and I mean, story becomes a little bit boring. So G minus is L prime minuscule. So this is the context in which I believe it's natural to consider this story about grand unification theories. Now I want to study the geometry of the corresponding minuscule variety. So we have this minuscule descent for representations, but of course we also have some minuscule descent for varieties. So we have here some line bundle is denoted Lx, and the minuscule descent will transfer it to a new group, which is L prime, new variety, which I will denote usually by Z, and some line bundle Lz. Examples of this minuscule descent are when we consider this vertex, then the corresponding variety X is a quadric, even dimensional quadric. So X say 2D with the action of the orthogonal group on it, and the minuscule descent sends this guy into X to D minus 2. I mean, another quadric, let's denote it just by X. So Q, X is Q, quadric, degree 2. So this quadric just comes into this one. The one which is by 2 is less by 2. The dimension is less than by 2. And of course, all these guys were also minuscule descent. So we have some E7 for E series, for example, we have E7 variety. Let's denote it by X E7. So we have descent takes it some E6 variety, and this goes actually the next one, the one which corresponds to this vertex, is orthogonal Grossmanian. Oh, sorry, I can write it here. So it's orthogonal Grossmanian of maximal isotropic subspaces in this D. So n here is 2D plus 2, I believe. Oh, well, I'm sorry. Anyway, it's orthogonal Grossmanian, doesn't matter. I mean, this n not the same as this D, so it's okay. And not the same as this one, so let's denote it by K. So it's k-dimensional isotropic subspaces in 2k-dimensional Grossmanian, which means that for this grand unification theory, the corresponding variety is the orthogonal Grossmanian 510. Now, as I said, for a n case, all weights are minuscule. So to the weight omega k, the corresponding minuscule variety is Grossmanian kn. Do we have anything else? No. So one can ask the question, what is the minuscule descent of the Grossmanian? And the answer is, if you take Grossmanian kn, then the corresponding variety is P projective space pkn minus 1 multiplied by Pn minus 1. And the reason is that we take this Dynkin diagram, we look at the case naught, we remove it, so we got two pieces, and that's why the group becomes the product of SLK, product of SLN, SLN minus K minus 1. It is SLN minus K. So because we have these two pieces, and the variety is this one with the action of this group. So it's a product. In fact, you can make minuscule descent even of this variety, but then there you will get several components, so one should a little bit adjust the definition of minuscule variety, calling it multi-minuscule and multi-minuscule descent, so I don't bother about this. All right, so we have we have this descent. My main point is that geometry of X could be described in terms of cohomology of Z, which is a little bit strange thing. So Z is this descent. To understand this, we need to degenerate this minuscule variety into toric variety. Right. So such a degeneration is some toric variety. There is a nice degeneration constructed by two authors. One of them have a Romanian name which is not reproducible. It's gone. I don't know how to pronounce it. English-speaking people say they don't know either. The other one is simpler. It's Lakshmi Bai. At least clear how to pronounce. All right. So what they constructed this degeneration. We just used the defining relations. It's known that X is a quadratic variety. Oh yes, maybe I should explain that in fact there is a geometric meaning for this minuscule descent. In fact, we have our X embedded in the projective space, some Pn, right? And we can take just one point in here and consider the tangent space, projective tangent space at this point x0. So we intersect it with the X itself inside this projective space. And this is actually our variety Z. So it's the variety of lines coming through a given point. So we have our X. Because it's given by quadrics, it's clear that this variety is a cone. I'm sorry. So this variety is actually a cone over Z. I mean, if you have variety given by quadratic equations, then the intersection of tangent space with the variety itself is given by is actually a cone, and this is a cone over our variety Z. So geometrically, it's the variety of lines through a given point, variety of lines on X. So it's now if we so they constructed this degeneration. The point is that one can write down equations for this X relatively explicitly. But for this we need some combinatorics. So let's consider introduce some partially ordered set X. What is this? We consider all these weights. So we have our representation V and which is the sum of v chi, where chi is an element of some set S. And this gamma x, as I said, is just this S. So this the set of weights of our representation. And there is a partial order. We can say that chi1 is greater than or equal to chi2 if the difference chi1 minus chi2 is the sum of ni alpha I, such that ni are positive integers, non-negative, and alpha I are positive roots. So it's the standard order. Standard order on this set. So we got some partially ordered set. So my claim is that if we consider minuscule descent, so we start from x, we take this minuscule descent and we come to z and consider gamma z, that this partially ordered set gamma z controls geometry of x in a little bit non-trivial way. There is a relation between gamma z and gamma x. If you have a partially ordered set, then you can say gamma is a partially ordered set. Then one can consider I gamma, which is the partially ordered set of ideals. Ideals in gamma. So you can ideal is a subset which, together with every element, contains all descendants of this element. So the claim is that the fact that gamma x is the set of ideals in gamma z. This fact is purely combinatorial fact, and in fact combinatorial people probably first found it, though I'm not sure they considered all minuscule cases. Again, this fact is true only for minuscule varieties. And it has some cohomological meaning. Well, first of all, there is some geometric Satake correspondence. Which identifies cohomology. It's basically cohomology of x is identified with this representation V. It's a little bit more subtle, in fact, because Satake correspondence is something about Lagrange duality. So we start from representation V, minuscule representation V, and consider the corresponding group G, and then there is a transfer from this group to Lagrange dual group, and there is a transfer from variety X to also to dual X check, which is basically the same node. I mean, this Lagrange duality, if you have some Dynkin diagram, you just invert all arrows on the diagram. But because we had no arrows on the diagram, it's simply laced case, so the group is themselves. And if you consider what happens with the with the weights, then if you have a weight, then you should take the same weight, but for this reverse diagram. So it's the same weight, the same diagram, meaning it's the same variety. And for that reason, the geometric Satake, well, in principle, you should take here the dual variety, Lagrange dual one. But because in our case X dual coincides with X, Lagrange dual, we have actually this isomorphism. So there is a cohomological interpretation of this vector space V. And also of this basis. And I mean, we have some maybe I didn't say that if you have minuscule representation, then all weight spaces are one-dimensional. It's obvious. And so we have some basis up to constants, and this basis could be identified with cohomology of our variety. That's one point. And the other point is that to prove this fact, one can check that if you consider appropriate cohomology using some BGG resolutions, then, well, you can see that these two guys coincide anyway. So there is some homological interpretation behind this fact, which probably need to be understood better. Now, so when you have this, now to understand this, this G word Lakshmi Bai degeneration, one should look at the defining equation of our variety X, and all of them look like this. So we have basis X gamma. It's a basis in this vector space V, or maybe better to take V dual. Global sections of our vector bundle, line bundle Lx. So equations of X itself is given by quadratic equations of this sort. So it's X gamma prime is equal to X gamma plus gamma prime, X gamma multiplied by gamma prime, plus the sum of some C. Maybe I'll write here alpha and beta. C gamma prime, and here X gamma prime, where gamma is less than alpha multiplied by beta, and gamma prime is bigger than alpha plus beta. So this product and sum is the union and intersection in this partially ordered set. The point is that partially ordered set is a lattice, meaning every two elements have the one which is lower than both, but bigger than any one. I mean, there is in the partially ordered set there is a notion of intersection and union. So the point is that from this fact it follows that this is a lattice, moreover it's distributive lattice. So we have this intersection and union, and this is the notation for these operations. And then degeneration is just by acting by one-dimensional torus on our projective space in which our variety is embedded. So x0 is given by these equations. It just can kill all this extra stuff. So this is Gonchileo Lakshmi Bai degeneration. GL degeneration. So now I will construct this degeneration in I identified with toric quiver varieties, and this describes the geometry of this degeneration in a much better way than just defining equations. This toric quiver varieties was, I think, the study of them was initiated by Lutz Hille, and then there is a paper by him and Altman. So we have some quiver Q. For simplicity, I assume that it has no oriented cycles and no relations, in fact. That's a nice thing that we will use quivers with no relations here to describe this toric degeneration. So Q is a quiver, and so it has Q0 and Q1, Q0 vertices and Q1 arrows. Then we consider moduli space. So we fix some dimension vector D, which is, every vertex has some number di over it. So we consider the space of representations of given dimension vector D. So this is dimension vector. So to describe this, it's a very simple thing. So we take all edges, all arrows in our quiver and consider the home space from CDI to CDJ. And then we have the group G, which is identified isomorphic representations. So this group is the product of GL CDI, where I is now in Q0. So the moduli space of representations, at least morally, is the quotient of L over G. But to make the story more precise in mathematical terms, one needs to introduce stability condition, and this was elaborated by Alistair King. So, excuse me?
What is the toric variety of the degeneration?
I'm describing quiver variety. The toric variety will be toric quiver variety. So I need to introduce the stability condition, which is in this case just a function on the set of vertices with integer valued function. With the property that on our vector D, the one which we fixed here, it is 0. Then there is the moduli space M theta on D. That's the moduli space of theta semi-stable representations of the clear Q. So representation is theta semi-stable if every sub-representation of this cure has theta of sub-representation is smaller or equal than theta of the representation of self, which means 0. So if you have R prime, let's be M1 is in our M is stable if theta on M1 is less than or equal 0, because theta of M is 0. Theta of M is theta of D. So this is theta semi-stable representations, and the way how one can construct this moduli space, you just consider the algebra of RK theta, which is so this guy is polynomials P with the property that G star of P is theta on G to K to P, where P is a polynomial on this vector space L. So this is polynomial now. So we consider this theta semi-stable representation and theta.
Spectrum. I think you mean the broad shot.
Yeah, spectrum of this algebra, right? Thank you. Right, and theta on G. So we interpret this theta as a character of our group. So this is the product of determinants of Gi theta I. Right, now we need to consider particular stability condition to describe this variety X0, this GL. I don't think it's worked, in fact, right? No? So there is particularly nice stability condition considered by Hille and Altman and Hille, and this is the Euler characteristic. So as a function, it should be defined for any d. So we fixed our d, but we consider it's as a function of another d prime, and this is just the Euler characteristic of from d to d prime, meaning the alternating sum of dimensions of x groups over this quiver. There is actually only Holmes and first x groups from representations of dimension d into representation of dimension. That's not good notation. So R md to md prime, and this number does not depend on the choice of representation of a given dimension vectors. In fact, it's just the number of this function is. Yeah, now I choose particular d. D will be d0, and this is just the vector dimension, which is just 1 for every vertex. And then the corresponding variety m theta d0. What was the notation? M theta. Actually, for any theta, not only for the canonical one, this m theta d0 is a toric variety. Now the claim is that this x0 GL toric variety is actually this m theta canonical for d0 for some choice of q or q. Now I need to describe the quiver, and the quiver is directly related to this minuscule gamma z of minuscule descent variety. I'll show you how it works in an example. So let's take the Grant unification theory, which is G25. The x gut, which is this variety, and then the minuscule descent gives us the standard model variety, which is P1 cross P2. So we need to consider gamma z, which is in this case is this diagram with arrows in one of the directions. I mean, partially ordered set could be understood as a kind of oriented diagram. I don't want to call it quiver because quiver will be the dual one. So first I add to this diagram an extra. No, first I put it on the sphere. Say in this way. I add an extra vertex on the other side of the equator. And then I take the dual quiver. So I put one vertex here, another here, in the north pole and south pole, and I take the dual quiver like this one. So this is going to be my quiver Q. So if I write the picture of this Q, then it looks like this. We have 1, 2, 3, 4 points. 1, 2, 3, 4. There is 2 arrows from here to here, 1 and here. So this is the quiver which I need to take to identify in this theorem. So Q is the dual quiver. So this is theorem. That Q, which is taken in this theorem, is the dual to gamma z tilde. Tilde because I add an extra arrow and two extra arrows and 1 extra point there. So this is the gamma z tilde, and then I took the dual quiver Q. So this is the variety for which one should consider the moduli space of representations with this particular vector and with this canonical stability condition. So the claim is that this is degeneration. What is good in this, you have description of, say, irreducible divisors on this degeneration, and many other good things. For example, if you vary the stability condition, then you got the Krappen's resolution of this variety. And so I believe that in fact this skewer describes the geometry of the variety in a very good sense. Unfortunately, I haven't finished this description, so for that reason I transferred to description. I mean, this picture also allows to describe mirror symmetry for the minuscule varieties, and that's what I'm going to explain. Well, the point is very simple. If you have toric degeneration, so you have a toric fan of toric variety. And this fan gives you the formula for Landau-Ginzburg potential W. So this is Landau-Ginzburg potential, which is just the sum of monomials corresponding to edges of the fan. So it's the sum of edges E, and here we have monomial ME corresponding to this H. Well, the point is that edges of the fan are exactly reducible divisors, and the reducible divisors actually correspond just to arrows in this skewer, because you just annihilate in the representation, you annihilate the corresponding arrow, and you got an irreducible divisor, not necessarily a Cartier divisor. So monomials correspond to edges, and in fact these edges are the same as edges on gamma z tilde, right? Because it's just the Dürr graph. So it's the sum of sum over edges. Here was edges of the fan of toric polytope, but in fact it's just sum over edges of gamma z tilde. And what you should do, you just put any letter in vertices of this, not of this, of this skewer. So you have this skewer, if you remember, right? So we put some letters in here, and every edge gives you just the ratio of them. So the sum, say for this picture, the Landau-Ginzburg potential W is just the sum of edges of guys like this, Y over Z, Z over W, and so on. Yes, and there is two extra edges, this one and this one. This one gives you just W, and this one gives you, because it's the opposite direction, sorry, Y over Z. Yeah, this would give you 1 over X. So to this H1 will get 1 over X, so this is W. It's actually known for Grossmanians, but the point is that the story generalizes to all minuscule varieties. For Grossmanians, this kind of picture was in a battery of Kim, Swan Stratton, and somebody else's paper. But you no. But this works in general. In particular, one can write down solution for quantum differential equation. So if you consider quantum cohomology of this variety X, then there is T1 of X, which is an element in here, and quantum cohomology is an equation of this sort. You take T d over dt applied to some function phi, which takes values in this cohomology, and this is quantum multiplication by the canonical class. So this is quantum differential equation, and if you describe Ix, there is actually just unique analytic solution for this equation. in this extra parameter t. So phi depends on t, takes values in here. There is a unique solution with the property that I, the boundary condition that this guy is the class Poincare dual of the class of a point. Then solution of this equation. So this is the A model for X. For mirror symmetry, we should give description for this guy in terms of Landau-Ginzburg potential W. And mirror symmetry predicts that this is actually I mean, in fact, one can write down, I mean, this is a oscillating integral, so it's integral of the form exponent. So this function should be understood as a function on a torus. So it's a function on y with values in c. This is c star to n, which is dimension of our x. So because it's Laurent polynomial, it's defined on this torus. And we should take exponent of tw, right? And here take, in coordinates dy over y, we take the standard form here and integrate over y equal epsilon, over small torus in this guy. So this should give you, so this is called J function. And mirror symmetry predicts that this guy coincides with this one. One can give the explicit description for this Jx in terms of the corresponding Q gamma x. You just take, I mean, it's easy to get it from this formula. It's just the sum over all closed paths of any length here. I skip it. Thank you.
You had a principal G bundle and then an associated vector bundle.
Right.
And if you take the associated bundle whose fibers are these minuscule varieties X,
if you take E7 and then restrict it to the standard model, you got all these 5 representations, but with unfortunately multiplicity will be not 3. That's a problem. Am I answering your question?
no, just I was wondering if you take the space, and you take the principal bundle and then the associated bundle whose fibers are X.
All right, right. I think it makes sense. I mean, I gave this talk to physicists in the Institute of Physics and Mathematics of the Universe, and they, you know, got some. It boosts new. I mean, they forgot. They work on this instead. So it's basically coming from linear models. I mean, when this, if you write down Lagrangian in terms of this connection and this section, then it's linear in the section, right? But they considered also non-linear models until until string theory comes. But then it's like a tank destroyed everything. So now there is a revival of interests. Considering non-linear models, yes, along this minuscule varieties. There's Yanagido, who's now working on this. It hopefully makes sense.
Let's thank